Thank you for joining me today on today's topic about interactive scalable visualization for data discovery and interpretable AI. At my research group at Georgia Tech Polar Club of Data Science, we focus on working at the intersection of artificial intelligence and human intelligence with the goal of developing scalable interactive tools to help people make sense of large amount of data and complex models. And I would always like to begin my talk by thanking my students because the work that you're going to see today are all done by them. My PhD students, master students, and undergraduate students, and starting from top left, and some recent alum at the bottom. Our research group is focusing on two research thrusts these days, interpretable AI and secure AI. And today's topic is about interpretable AI, and I often like to motivate it using secure AI because then the connection is usually very clear and the need for interpretation is immediately obvious. For example, in our recent work with Intel, we developed the shapeshifter technique where we can fold a state-of-the-art object detector into misrecognizing a fake stop sign into pretty much anything that we want. For example, in this video, you'll see that the fake stop sign get misrecognized as a whole bunch of people. Then people might ask, so how do these techniques work? So how do we fold the object detector? Actually, no one really knows. So we know that the overall classification or recognition was wrong, but then exactly why it was wrong, like how the model was fooled, is still actually not very well known. For example, a lot of these techniques are based on deep neural networks. You may ask the question, okay, so exactly what neurons, what layers, or what connections are the attacks that they're exploiting, or when you have a defense, what is the defense really protecting? Actually, we don't really have a good handle on these fundamental questions. In other words, often these techniques are used as black boxes, and our goal is to try and open up these black boxes so they become more like a translucent boxes where we don't really necessarily tell people every single details that they may want to look at, but rather we help them find out what's the relevant, the interesting part so that can help them perform their task better. So in other words, we are using interactive scalable visualization to help people make sense of these complex models and data sets. And in today's talk, I'll share a few example projects that are exactly in this area. So I'll start off with a system called SUMMA and its related system called Bluff, which together they help people understand and interpret how some of these deep neural networks work. And after that, I will talk about a system called GAN Lab and CN Explainer. Both systems are designed to help both experts and also beginners to understand how the training process, also inference work in these models. And based on our experience on developing a lot of these web-based tools, which we will see, we found that the web platform is actually really a powerful and effective way to share and disseminate results. And for that, we developed the Argo Lite system, which is also using an in-browser implementation. But in this case, we're having people explore and visualize graphs directly in a web browser. And I'll end my talk with pointers to two surveys of open problems and also future research directions. SUMMA is one of our very first tools designed to help people interpret deep neural networks. And the main idea is that we want to help people understand what are the specific features that a deep neural network has learned and what are the connection among these features that will lead to the final classification. For example, here we're considering the ImageNet data set with 1,000 image classes. And we want to find out, let's say, for the class of white wolf, what are the features that would contribute to the classification of white wolf at the end. So conceptually, we want the network to be able to learn wolf features. So that's like their legs, their paws, their fur, ear, and so on. And also, some of these features are a lot more lower level. And how do these lower level features will build up hierarchically, iteratively into some high level features, and eventually, so how would they be used together to inform the final decision. So this is the kind of conceptual representation in a network form that we want SUMMA to be able to visualize and help people understand. So on the next screen, I'm going to show you a demo of SUMMA, and you can actually go to our website, fredholman.com, SUMMA, to try it while you are listening. And here I'm showing you the user interface SUMMA, and on the left-hand side, you see that I already picked the Tenge class, which is a kind of yellowfish out of the 1,000 image classes. And then on the right-hand side, this is the graphical representation that I was talking about. So each network and each neuron here is a feature that you can think of that the network has learned about the class. And the edges here are the connection among those features. And when you mouse over a neuron, you will see image patches that are examples from the actual data set to help you understand what a particular neuron or feature is learning. And as you go down to the lower level, like lower towards the bottom, you'll find that some of the features are actually about people. For example, like faces or hands and so on. And it's not until later layers or higher layers, more closer to the end, where we start to see a little bit more features about fish. And this is actually really surprising because the image classification that we're doing here is for tench, which is kind of fish. But then what we end up seeing is a lot of people. So that was really surprising to us, and caused us to go back into the data and then see like what is really happening. And to a surprise, we found that in the image set data set, most of the images in the tench class are actually about people. And it turned out that tench is the kind of fish that people like to catch and then take pictures of. So what that means is that even for this model, which is actually really accurate in classifying tench, 92.1% accuracy. So what it's really doing is to use these people feature to help with the classification of tench. And that raises the question, would you feel comfortable if you're trying to do image classification of tench? Would you feel comfortable using this model now that you know it's actually using a lot of images of people? Maybe yes, maybe no. So yes, if the data that you are going to be classifying actually are pictures of people and tench. Or maybe no, if your task is really only about fish, it's nothing about people, and actually having people could actually lower your task accuracy. So this is a really interesting finding, and this is to a surprise completely. SUMMA originally was designed to help people understand when the model is working well. So what it has learned and what the connections among the features it has learned. And through seeing the surprising example of tench, that actually got us thinking. So maybe we can use SUMMA to also understand when a model is not working well. So that motivated us to build the Bluff system, which you're seeing here as a screenshot. In particular, in Bluff, we allow people to pick different kind of attack that they want to apply on a model. For example, PGD, which stands for projected gradient descent, which is a common method that people like to study in adversarial machine learning literature. And the user can pick this attack and then run it on the model, and so that they can mislead the classification model into misclassifying, let's say in this case, a giant panda images into armadillo class. And so an interesting feature about Bluff, which is new, extended over SUMMA, is that it not only showed the connection using the same graphical representation strategies among these features and also the relationship, but also it specifically pinpoint what are the particular features or neurons that the attacks are exploiting. For example, to turn giant panda images into armadillo, what we need would be some bumpy or some scale kind of features. And in the Bluff system, we can exactly see which neurons are responsible for these bumpy features and scale features, and what are the pathways or the connections that are connecting these features that the attack is exploiting. Again, you can go to our URL up there and then try it yourself, and then try the different combination of benign classes and attack classes, and also change attack string to see how those parameters would affect the exploitation in the model. Both SUMMA and Bluff were systems that focus on helping people make sense of image classification model. And of course, there's a lot more different kind of models and tasks that we want to study. So in our recent SkeletonVis system that was published at AAAI as a demo, we help people understand how attacks on human action recognition models would work. And again, using interactive visualization, but in this case is to help people understand how, let's say, a skeleton that the human action recognition model would be using to do inference would be manipulated by an attack. So in green here is a benign skeleton. So that means without attack, like what would the skeleton look like for, let's say, the lunge classes, a person doing lunge. And then for orange is the manipulated skeleton by the attack. So we will see that in some frames, but not all frames, where the skeletons actually get manipulated in ways that are humanly impossible. And this is actually really interesting and helpful to recognize, because when people study this attack, all they were seeing is actually just a number, the outcome that, oh, so our attack is successful, here's the accuracy that has dropped, but then exactly why this accuracy drop is not really clear. For example, when we say there's a skeleton distorted that we see through this visualizations, actually it wasn't clear that there was any kind of distortion at all. So or it wasn't clear that how many frames that this attack really manipulating and to what extent. So a visualization like SkeletonVis help us understand what these attacks are actually doing and how they manipulate the model and what kind of features that these attacks are exploiting. While building the SUMMA tool, Bluff, and SkeletonVis, we work with a lot of machine learning experts. And we found that visualization is helpful not only for beginners, but also for experts. And that motivated us to develop the GAN system with Google, where we use visualization to help experts understand how training process of deep generative networks would work. And you may have heard of GAN or generative adversarial networks a lot these days, because it's one of the fundamental technology that enable techniques like deepfake, which can generate realistic looking data that are actually fake. For example, faces that look really real, but they're actually fake. So you may ask why we pick GAN. So why is it hard to learn GAN? So it turned out it's because GAN has two competing neural networks inside it. So what that means is that if you were to train a GAN, you're actually training two neural networks that are competing. They're iteratively improving based on each other's performance. So to explain that, I would like to use an everyday example of, let's say, a counterfeiter trying to make fake bills, and then a police trying to catch these counterfeiter. So internal to a GAN, counterfeiter would be called the generator that generates fake data with the goal of making the fake data looking as realistic as possible, kind of like making fake bills that can fool the police. While for the police, in the GAN, it will be called a discriminator. So it's able to tell apart the fake and the real bill. And training GAN is an iterative process. So it's kind of like a counterfeiter. So initially, when the counterfeiter trying to generate a fake bill, they don't look really that good. So the police have a really easy time in telling them apart. Of course, the police would have access to the real bill so that it can compare the difference and do the classification. And of course, the counterfeiter will improve over time. Right? Once the counterfeiter get caught, then it's, oh, well, okay, so these are not good enough, so I'm going to make the fake bill look more realistic, better. And at the same time, the police would also improve, because then as the fake bill look more realistic, then the classification task becomes harder, so that police also need to become better at distinguishing. So this is what's happening in conceptually. And of course, in GAN, there are a lot more happening technically. And particularly, we found that using this kind of conceptual model, using these two specific components and visualizing the iterative flow of these two components, how they improve and how does the data flow, how the decision boundary would change over time, and also allowing users to change the hyperparameters of this model. It turned out to be a really effective way to help experts and beginners to understand the training process. So when we released GAN, which is a design based on what I just described, using these components and the flow, the tool went viral because it turned out it's one of the very first approach to visualize the training process and help explaining the training process this way. And a lot of excitement around the tool, and it got a lot of likes and a lot of stars on GitHub. And also there's something that I think was really exciting to us, is it makes us recognize that this kind of web-based delivery of a tool is a very powerful and efficient way to disseminate our research. And particularly we think that, well, if this is a technique that would work for GAN, so maybe it will work for other deep model as well. So that got us thinking, well, so GAN is actually a pretty complex model. What if we go with something simpler? So let's say some of the techniques that beginners or maybe students new to deep learning would like to learn. So we then look at, well, CNN is actually one of the first techniques that people want to learn. Actually, it's also one of the techniques that I needed to learn when I started working with my students on building visualization for deep learning. So we said, okay, so we're going to pick CNN Explainer. So how would we want to do it? So I said, well, so if we the approach for GAN Lab worked really well, so maybe we can do the same thing for CNN Explainer. So that's what we did. So we built a web-based interface where we're using, trying to use a simple model. This is a toy model on only a few classes, 10 classes, where our goal here is not really to explain the precise accuracies or the training process of CNN, but rather we want to help students and beginners understand how an image would pass through a network, like what are the precise mathematical function, the steps, that's happening, and also to explain that very intuitively, so that in some ways to connect the textual description that often students would see in textbooks or maybe in lectures, but then they don't really get to see the interactive aspect or the visualization of how those mathematical function and description would get translated. So in other words, CNN Explainer is one single tool, interactive visualization tool, where the students and beginners can get to see everything all at once in one interface. They can zoom in, they can zoom into the detail, and then also zoom out, look at the overview of the project, and then they play with it. So I encourage you to also try out CNN Explainer at the URL up there. And also when we released CNN Explainer, it also was really exciting and it went viral, and then also got a lot of stars and likes on social media and on GitHub. And our experience with building web-based tools for deep learning made us realize that this is actually a really general strategy that we can use not only for deep learning, but also generally for data exploration and visualization. And that motivated us to develop the Argo Lite tool, which was published last year at CIKM. It's a completely web-based a visualization tool for graph data, where a user, again, can go to just a URL and they don't need to install anything on their machine, and they work on both desktop and mobile devices, where they just go there and then they can load in graph data and then do incremental exploration, visualization, and also even better, they can share their visualization result as a URL with anyone, and also to embed that into any application that you want. Or they can go to the same URL and then continue working on it. So we see that more and more tools in the future will be built using this strategy. And definitely from our group, we'll continue to extend this approach for more systems. So today I've shared a number of projects in our group about using interactive visualization to help with data discovery and also interpretable AI. And of course, there's also many projects that we haven't mentioned. So to end this talk, I'd like to point you to two very interesting surveys, which describe some of the open problems and also some future research directions that you may want to look at. And on the left, that is a very interesting survey, a comparative survey for human AI interaction guidelines. And this is very interesting because this is actually a summary comparison of guidelines from tech companies like Microsoft, Google, and Apple. And they are all trying to release some guidelines that they suggest practitioners and researchers would try to follow and when they're deploying AI in their technology systems. And the interesting aspect is that even though they're all about guidelines, but you'll see that not every company agree on the same thing. So of course, there's also quite a bit of overlap in the guidelines that's proposed, but also quite a lot of difference. For example, one company may focus on more guidelines surrounding, let's say, mental model, where another company may be focusing more on the technical aspect of these guidelines. And then on the right-hand side, that is another a very comprehensive survey where we summarize the state-of-the-art of visual analytics for deep learning. And we particularly were using the 5W and H model. So that means for each paper that we survey, we want to look at why it was developed, like for whom, which users, what are the particular approach, the how part, and then how it's applied and what process of machine learning or deep learning process. So in other words, we did all the work for you, and so that you can just look at the summary that we generated. So with that, I'd like to thank you today for joining me in today's talk. And if you have more questions, so please send me an email, and of course also check out our website, because all our information are there, and also the project that I presented, they're all there, so the paper PDF, videos, and demos. Thank you very much.